Hello everyone, I am Pavitra GS, Assistant Professor, Department of ECE, Sai Vidya Institute of Technology. Subject name is Digital System Design. Subject code is 18EC34. We are going to start with Module 1, Principles of Combinational Logic Circuits. We see what we learn in this Module 1, that is Principles of Combinational Logic Circuits. We learn the definition of combinational logic circuit, the different types of canonical forms, how to generate the Boolean expressions from truth tables, and simplifying the Boolean expressions using K-maps for 3 variable, 4 variable, 5 variable Boolean functions, including the don't care terms, that is incompletely specified functions. And also we learn how to simplify max term equations and using tabular method, that is Quinn-McCluskey technique, how to simplify the Boolean functions. After we learn module 1, a student will be able to gain knowledge on the combinational logic circuits, simplification techniques using K-maps and algorithms. To begin with the introduction of principles of combinational logic circuit, we start to analyze or to understand what is digital circuits. So the word digital means data expressed as series of ones and zeros. So all the information will be represented in terms of ones and zeros in series. So that is what we call as digital. Now we learn what is circuit. Circuit will perform some operation. It can be either analog operation or it can be a digital operation. In terms of analog operation, that is the input will be given in terms of analog, and in terms of digital circuits we perform operation based on the digital input, that is ones and zeros. So the digital circuits perform operation on digital data, that is series of ones and zeros. So based on this we have two types of digital circuits. One is combinational logic circuits and another one is sequential logic circuits. Let us now see what are combinational logic circuits. The figure shows the block representation of combinational logic circuit where it consists of n input variables and m output variables. So the combinational logic circuits comprises of n input variables, a combination of logic gates and m output variables. The output of the combinational logic circuits depends on the values of the applied input at any instant of time. So if you are observing some change in the output, definitely there will be some change at the applied inputs. Combinational logic circuits do not have any memory. It means that it does not have capacity to store the data. So as and when you change the input value, accordingly the output also changes. So the logic circuit here is constructed by combination of logic gates. Some of the examples of combinational logic circuits are adders, comparators, and decoders. Next we will see what are sequential logic circuits. The block representation of sequential logic circuits is as shown here. It consists of two blocks, the combinational logic block as well as a memory block. The memory elements are given as a feedback to the combinational logic circuit here. A sequential circuit comprises of n input variables, logic gates and m output variables. The output of the sequential circuit depends on the applied inputs as well as the memory elements. So we can call the memory elements to be as a previous states. The sequential circuits have memory and also the feedback. So these memory elements are nothing but the flip-flops. The logic network is constructed by the combination of the logic gates. The examples of sequential logic circuits are flip-flops and counters. Next, we will see the general digital logic design procedure. To design any digital system, the problem statement has to be defined properly. So the analysis of problem statement gives you the total number of input variables and total number of output variables required to perform some operation in the system. So the second step is to construct a truth table. So truth table is a tabular representation which defines the relationship between input variables as well as output variables. So next comes deriving the logical expressions from the output column from the truth table. So after deriving the logical expressions, these logical expressions can be represented in different types of digital expressions. It need not be a single form. It can be represented in different forms. Now, after representing the logical expression, then the next step comes the simplification of the logical expression. So simplification of logical expressions are very much important in order to reduce the cost for the implementation, and we have different techniques for simplifying the logical expressions, such as we use K-maps for simplification, we use algorithmic methods such as Quinn-McCluskey algorithm for simplification of Boolean expressions. After we obtain the simplified expression, next step is to draw the logic diagram using different logic gates and to build the logic circuit using different technologies such as the CMOS technology or TTL technologies in the hardware. So this will be the general procedure for designing a digital system. Next, we will see what is a truth table. So, truth table is a tabular representation for a Boolean expressions. It can define some operation in which it consists of both input variables of a system as well as the output variables of a system. So, let us now define the truth table and understand how to write the truth table for a simple logic gate function. So, we have considered here as a two input AND gate function where it has two inputs A and B and output as Q. Now the input variables are defined as A and B and output variable is defined as Q here, and the operation is AND operation. Now let us represent the truth table. Truth table consists of the columns which is defined for input variables and also for the output variables. Now the input variables are A and B, so we write A and B column here, and output variable is Q, therefore we write output column as Q. For two input variables, we have 2 power 2 combinations, that is 0, 0, 0, 1, 1, 0 and 1, 1. For these four combinations, let us now derive the output column, that is output variable Q for different combinations of input variables. The AND operation for 0 and 0 is 0, 0 and 1 is 0, 1 and 0 is 0, 1 and 1 is 1. This is how you represent the truth table for any logic gate function, or it can be represented for different digital systems. So we have, if we have n input variables, then 2 power n combinations has to be defined in the truth table. For example, if n equal to 2, 2 power 2 equal to 4 combinations should be defined in the truth table. If n is equal to 3, 2 power 3 equal to 8 combinations to be defined in the truth table. Now let us see, for a given truth table of a Boolean function f, how do we implement the truth table using logic gates? So we have a truth table here. Now let us see how to implement or what logic gates has to be used for implementing this particular truth table. Okay, the first questions arises is, what is the logical expression of f? How to write the logical expression of f? The second question arises is, what is the gate implementation of function f? Now, to answer these questions, we need to define both minterms and maxterms in order to write the gate implementation as well as the logical expression. So, before we write these two, we should first understand the two different terms, that is minterm and maxterm. Now, let us see what are minterms and maxterms. We'll first define or understand what are minterms. Minterms are product terms with every input variable present in either complementary or uncomplementary form. So please remember, minterm is a product term. It may consist of both the complementary or uncomplementary variables. Second term is the max term. Max term is a sum term with every input variable present in either complementary or uncomplimentary form. Let us now see what are how to represent different min terms and max terms. Before we write the expressions, first let us learn how to represent binary value 1 and 0 in minterms and 1 and 0 in maxterms. So first here we have for minterms, 1 is represented by a variable which is considered as uncomplementary. For minterm, 1 will be considered as a variable in uncomplementary form. Okay, 0 will be considered as a variable as complementary form. Suppose if we have the variable as x, 1 will be considered as x, 0 will be considered as x bar representation. Similarly, for max terms, 1 is considered as the variable is complementary and 0 is considered as the variable is uncomplementary. Now, we shall see the minterms and maxterms for two variables x and y. So, we have a simple table here which represents both variables x and y for four different combinations, and we have defined the index also here. So, index we have four different combination. Index is 0, 1, 2, 3. We have defined for index for each of the combination. Now, let us write the minterms and maxterms. First, let us concentrate on minterms, then we go for the maxterms. Already we have seen minterm first is represented as a product term. Minterms are represented as a product terms where 1 is considered as uncomplimentary, 0 is considered as complementary. The same concept will apply here and write the minterms. So remember, minterms are product terms. Let's start with the first combination. X is 0 and y is 0. So 0 in representing minterm will be considered as a complementary variable. Therefore, as minterm is a product term, we can write this as x bar, y bar. Next combination is 0, 1. 0 is complementary, 1 is uncomplimentary while representing minterm. Minterm is a product term, therefore we can write this as x bar, y. Next combination is 1, 0. 1 is uncomplimentary, 0 is complementary. Minterm is a product term, therefore M2 is defined as x, y bar. Next combination is 1 and 1. 1 and 1 both are uncomplimentary in minterm representation. Minterm is a product term, therefore M3 will be x dot y. So this is how you represent the minterms for two variables x and y. And also the notation representing the minterms is small m notation along with the index here. So you can see the minterms are represented by small m notation. Now let us see the representation of max terms. Max terms, already we have discussed that it is a sum term. Okay, max term is a sum term where 1 will be considered as complementary, 0 will be considered as uncomplimentary while representing a max term. Now let us see how to represent the max terms for two variables x and y. Now let us first concentrate on this, that is the last column representing max term, and look into the input variable values x and y. Let's start with the first combination, x equal to 0, y equal to 0. Therefore, 0 while representing max term is an uncomplimentary variable and max term is a sum term. Therefore, capital M naught, max term is represented by capital M. Capital M naught equal to x plus y. Okay. Now, let's go for the second combination, that is 0 and 1. 0 is uncomplimentary, 1 is complementary in representing max term. Max term is a sum term, therefore M1 will be equal to x plus y bar. Next, we go for the next combination, that is 1, 0. 1 is complementary, 0 is uncomplimentary. Max term is a sum term, therefore M2 equal to x bar plus y. The last combination is 1, 1. 1 is represented as a complementary variable. Therefore, for last combination, as max term is a sum term, we can write M3 equal to x bar plus y bar. This is how you represent both minterm and max term. Next, we will have a look on minterms and max terms for three three variables x, y, and z. So for three variables, how many combinations we can obtain? It is 2 power 3, 2 power n. N will be the total number of variables. So the total number of variables here we are considering it as x, y, z, that is three variables. Therefore, 2 power 3 gives you 8 combinations starting from index 0 to 7. So, we have two separate columns which are representing separately the min terms and max terms, and we have already discussed in the previous slide that min term is a product term and max term is a sum term, and 0 is considered as a complementary in min term representation, 1 is considered as a uncomplementary in min term representation. Similarly, for max term, 0 is considered as uncomplementary variable, 1 is considered as a complementary variable, and it is a sum term. So, we have different representation for different combination of min terms and max terms here. And next, coming to the relationship between the min term and max term here. So, we can define the relationship between min term and max term as, suppose if you consider a max term, I indicates the index, okay. So, capital M representation is max term representation. So, complement of max term will give you the min term. Complement of max term will give you the min term. Complement of min term will give you the max term. Okay, that defines the relationship between the min term and max term. Now, in this session, we have studied the definition for combinational logic circuit and how the combination logic circuit behaves, the general design procedure for combinational logic circuit, and we have learned to represent the two types of terms, that is min terms and max terms. Thank you.